All right, so welcome back. We are in Chapter 2, Section 2. We're going to study the power rule, which the good news is we get to bypass a lot of that tedious work that we were doing in 2.1, where we were using the limit definition for a derivative. What we're going to be studying over the next few sections is the shortcuts, or the recipes, if you will, the formulas that bypass a lot of that tedious analytical work that we were going through. I do want you to understand that that definition, the 2.1, if every derivative that we take in this class, you could have taken it using the limit definition. Okay, but let's go ahead and proceed. So there's two rules. The title of this chapter is the power rule, but I'm going to introduce two rules to you at this point. So let's start with the first. And it's a pretty simple statement that the derivative of any constant is equal to 0. Now, intuitively, I could show you the graph, and we could address why this makes perfect sense just intuitively through the graph. But what I'm going to do is I'm going to show you how, if you were to try to apply the limit definition to this function, why you would get 0 no matter what constant you choose, right? So a constant meaning like 3, any number, pi, any constant that you choose, the derivative of that constant would be 0. The proof of this is fairly simple. So let's begin. If you were to start with the difference quotient, remember the first thing we did is plug x plus delta x in, right? We plug it in for what? Well, we plug it in for the variable x, but there is no variable, right? So f of x plus delta x is just the same as f of x, which is just the same as c. So what we have at this point is the limit as delta x approaches 0. And let me go ahead and state that again. There's nowhere to put an x plus delta x. There's no variable on the right side of this equation. So let's just go ahead and write it. So that would just be c. All right. Now we want to subtract f of x. So we want to then subtract c. All right, well, we see that any constant minus itself is going to be 0. So we end up with the statement 0 over delta x. Now, the key here is that you want to evaluate the limit, meaning plug in the limit after you've simplified your problem. So 0 divided by some non-zero constant, delta x, just means we have the limit as delta x approaches 0 of the constant 0, right? 0 divided by, I hope that I didn't say that too quickly. I understand for all intents and purposes, delta x is 0. Please understand that what we're really saying is that delta x is a distance between two numbers. And we're saying that we are choosing a distance that is so infinitesimally small that it is, for our purposes, indistinguishable from having a distance of 0. But it does have a distance greater than 0. That's the only way this works. But we know from chapter 1 that the limit of a constant is just the constant. So the limit of delta x approaching 0 of 0 is just equal to 0. So you are safe to, anytime you take the derivative of any constant, to just write 0. Now, for the power rule for part B, there are a few different proofs I could show you. A couple of them are fairly tedious to walk through, but they don't require any prior calculus knowledge to get there. The third one, which is the short one, is the one that I'm going to show you. It's just, unfortunately, it calls upon a definition that you haven't been exposed to yet. So if you will allow me, if you will just trust me, there will be one step in here that, again, you'll just have to trust that I've written it correctly. So we'll begin with, let's define y to be equal to x to the power of n. And what we're going to do is we're going to take the natural log, ln, of both sides of this equation. So ln of y, ln of x to the power of n. Now, the natural log, ln, is just it's a logarithm, really quickly, just so you know. So normally, if you have log of x, right, you have an ln button on your calculator, a log button on your calculator. If you don't see a subscript under the log, then it's assumed that it's log base 10. Okay, if you see some other subscript, then it's, say, log base 2 or something else. ln is just the ln, the natural log, is just a logarithm, okay? But it's a logarithm with a base of e. Okay. So now what I want to do is go ahead and apply some of the log rules. And one of the log rules says that you can take the exponent and bring it out in front of the log. Okay? So we get to turn this into an algebraic, or at least if you were solving for n, you turn this problem into one that is algebraic, which allows us to use some properties of algebra. So we can rewrite this as ln of y is now equal to n times ln of x. Okay, so what just happened? Well, nothing special. I just took the n and brought it out front. Okay, so here's the part where you'll have to just trust me. I'm going to take the derivative of both sides. So since I'm taking the derivative of a y variable with respect to an x variable, I would get y prime over y. And then taking the derivative of ln of x would leave me with 1 over x. Okay, so we're almost there. I know a lot of you don't like the idea of proofs, but we're almost there. So just 2 more steps, and I believe that 2 or 3 more steps at tops will arrive at our answer. So what I'm going to do is I'm going to take this y variable and just bring it over to the right-hand side of the equation, right? So in other words, I'm multiplying both sides of this equation by y, so that the y's cancel on this side, and I'm bringing y to the right side. So let me do that now. So that would leave me with y prime being equal to, and I'm going to write this as n times y over x. Okay, if you're thinking, well, you could have wrote that as n times y over x, you're spot on. I did this purposefully, and you'll see why in just a second, okay? So what we're going to do right now, because I think you'll agree with me, this does not look like this. But here's the good news. We know that y is defined as x to the power of n. Okay, so wherever I see an x to the power of n, I could substitute a y. Wherever I see a y, I could substitute an x to the power of n, because we've defined them to be equal. So let me just go ahead and do that right now. I'm just going to substitute this x to the power of n in here for y. All right, so now we would have n times x to the power of n over x. And let's finish it. Last step. So x to the power of n divided by x to the power of 1, right? Well, when if I were to have x to the power of 3 divided by x to the power of 2, you know that that's just x to the power of 3 minus 2. When you have like bases, you subtract the exponents. So in this case, y prime is going to be equal to n times x to the power of, well, like bases, so subtract the exponents. So n minus 1. There you go. So now the next few problems, we're just going to practice these two rules, okay? More importantly, if you are starting to get sleepy already, please wake up when we do, well, actually, yeah, wake up when we do problem number 7 and 9, because I just want to make sure you get this rewriting portion of a problem. So, all right, number 3. So we have y is defined as the constant 12. Well, and what do you want to do? You want to find the derivative, y prime. Well, the derivative of a constant is 0, so we're all done. All right, for number 5, we have y is equal to x to the power of 7. Now, again, using our power rule, let's let n, in this case, our n is equal to 7, right? Our exponent is 7. So, our derivative, y prime, we're going to bring that exponent out front. So 7 x to the power of, now it's 7 minus 1. Okay, so this, let's go ahead and finish it. So y prime is therefore equal to 7x to the power of 6. You are welcome to jump from this step to this step, okay? I was just, so that you have notes, good notes for your quizzes and tests, or actually just your tests, depending on which one of my classes you're in. We are done with number 5. So number 7, so we have y is equal to 1 over x to the power of 5. Now, if you give me, a lot of times if you give me two calculus students working the same problem, and student 1 is working really, really hard, right? I mean, they're going through many, many steps to get to the solution. Student 2 just seems to be seamlessly arriving at the solution with not a lot of work. I will guarantee you that 9 out of 10 times, the second student just simply noticed that they could rewrite the function. So look what I'm going to do. I have y is equal to 1 over x to the power of 5. I can rewrite that as y being equal to x to the power of negative 5. Right? There's no calculus yet. I just rewrote the function before I take the derivative. So let's take the derivative. So in this case, we have n is equal to negative 5. So now let's take our derivative. So y prime is going to be negative 5 x to the power of negative 5 minus 1. You will be surprised at, even at your level of mathematics, the silly mistakes that I see. So, for example, negative 5. Well, if you have negative 5 minus 1, right, you owe me $5, you borrow another $1, you have x to the power of negative 6. You don't know how many students, even in higher maths, right, will still make silly mistakes like writing negative 5 minus 1 is negative 4. Okay? All right, so I want to say two quick things. First is the most important part is I want you, and I need you, I'll take off points if you do not, I need you to rewrite all of your solutions without negative exponents, right? So I don't care about the coefficient being negative, that doesn't bother me, but I don't want negative exponents in your problem, and you'll have to believe me when I say that this is for your own good, because where we want to go with derivatives is we want to be able to use them. We want to be able to start setting them equal to things, and what I'm telling you is life is so much easier if you just get into the habit of changing your exponents from negative exponents to positive exponents. So here would be the way you would write your answer. It would be y prime is going to be equal to negative 5, and I'm going to bring that x to the negative 6. I'm going to move it to the denominator so that I have x to the power of positive 6. All right, and now at that stage, we are done with that problem. Now let's do number 9, and again, so just again back to my story about the two calculus students. So one is trying some chain rule or other different types of rules to take a derivative, and the former student is just noticing, hey, wait a minute, the fifth root of x, that's the same thing as x to the power of 1/5. So now we can apply our power rule. So again, the derivative, f prime of x, that would be 1/5, n being 1/5, x to the power of 1/5 minus 1. All right, so let's finish this. So that's 1/5 x to the power of, well, if you have 20 cents and you take away $1, you now have negative 80 cents, right? So you have negative 4/5. Okay, again, to appease your professor, let's rewrite this without any negative exponents. So that's 1 over 5x to the power of 4/5. Okay. So we're done. Now, if you would like, you can always try 4 through 10 before we move any further, but you can double check your work in compared to the 4 problems we previously did. I don't think you'll have any trouble with those. But let's now continue our study. So let's do something here. Let's start to pay attention to the language that's being used. Because if you have a bad habit of freezing up during math tests, I guarantee you this is why you're freezing up during math tests. You're doing stuff like this, not paying attention to what it is you're doing, okay? So let's read. It says, find the slope of the graph of f of x is equal to x to the power of 4. So I've went ahead and I've presented the graph of this is x to the power of 4. And then it asks us for each of the following x values. So let's really quickly. When in doubt in a calculus class, take a derivative. So if you want to find the slope of something, you should automatically be thinking, okay, then that means I'm going to need the derivative, f prime of x. I'm going to change that color just so it's a little bit easier on the eyes. So f prime of x. Well, the good thing is this is an easy derivative. This would be 4x to the power of 3. Okay, so step 1 is done. We now have the derivative. And what is a derivative? Right, well, the derivative is just a function, right? See, this is a function of in this case, function of x. And its job is to give you a slope, a rate of change at some line tangent to a curve at some point. All that means is this is a function that generates slopes, okay? Now, the finish it, so part A, part B, part C, it is that simple as plugging in the x values. So that's all that I'm going to do for each of these is plug in these x values into my my derivative. So let's go ahead and write that. So for part A, this would be f prime of -1. For part B, this would be f prime of 0. For part C, this would be f prime of +1. So I'm plugging in my x value into my derivative. And let's see what comes back out. So this would be 4 times -1 to the power of 3. This would be 4 times 0 to the power of 3. And this would be 4 times 1 to the power of 3. All right, well, -1 to the power of 3 is -1 times 4 is -4. And 0 cubed is 0 times 4 is 0. And, of course, 1 to the power of 3 is 1 times 4 is 4. Okay, so it would be a shame to be able to pass a calculus class and not understand what you did the entirety of the time. So what are these values? Yes, they are the slopes of well, they are slopes. That is true. We evaluated a derivative. But let's go back to this graph. Okay. So notice that this graph that I've produced for you, this is not the graph of the derivative. That would look different. This is the graph of the original function. And I have the 3 points that we are interested in. -1, 1, 1, 1, and 0, 0. So, if you wanted, so for example, let's start with -1. Now, I won't do this for each one, but I'll do this for -1. So notice that, so we have x is equal to -1 here, okay? So notice what each function does for you. If you want the y value at when x is -1, then you plug -1 in for the original function. So here is the y value, -1, 1. But if you want to know the instantaneous rate of change, right? If you want to know the slope when x is -1, you plug that -1 into your derivative. And what that's doing is you can now think of it as, my apologies here, all over the place. So we now think of it as a tangent line and the only thing that that tangent line and that curve have in common is this one point here. That's all. That's it. That's what they have in common. So if you know that the slope of that tangent line is -4, right? Well, then that would mean that the slope of every single point on this tangent line is -4. So that would mean that the slope at this particular point is also -4. You could do the same for each one of these. You could draw tangent lines, but the geometry is important, because, especially for me, to intuit what it is that we're trying to do. Okay, this is an important problem, so you might want to highlight it or take a second, pause it, write it in its entirety if you want. Now, let me read. So it says, find an equation of the tangent line. All right, let me read it all first. So find an equation of the tangent line to the graph of f of x equals x squared when x is equal to -2. All right, ready? So let's play some association here. When you read find equation of a tangent line, here's what I want you to think. Your answer should be y equals mx plus b. That's the equation of a line, and that's what it is that we're looking for. So hold on, let's go back to algebra class. Recall that to get the normal steps to get to y equals mx plus b, well, it required some information, right? We would normally use the point slope and this point slope formula was an intermediate step to get to the equation y equals mx plus b. Now, what was the requirements that we needed to use? To use the point slope formula? Well, it's the title reveals it, right? To use the point slope formula, you need a point, right? Some xy point, and you need a slope. So if you have a point and a slope, then you can get an equation of a line. So, all right, so hold on for a second. Let's go back to what we have. Well, do we have a slope? No. No, there's nothing in here that gives us the slope. Do we have a point? No, but we do know the x value of the point, right? We know that x is -2. My apologies if my air conditioner is in the background is a little bit loud, but unfortunately, you'll have to deal with it. So I don't. I'm not super uncomfortable when I'm recording these videos. So all that I know is the x value. So here's the point that's of interest, and I know the x value of this point. I don't know the y value yet. Okay. Now, if I want a slope, then hopefully you're thinking, oh, wait a minute, I'm definitely going to have to take a derivative if I'm going to need a slope. So let's rewrite. So f of x is x squared. Okay, let's take our derivative. So then f prime of x is equal to 2x. All right. So we have two functions, and we need two pieces of information. Well, the original function, if you give it an x, it will give you a y. Okay? The second function, if you give it an x, it'll give you a slope. So let's go ahead and finish this. So f of 2, f of negative 2. I'm plugging negative 2 in to the original function. So this would be negative 2 squared. So f of negative 2 is positive 4. Okay, good. So I now know that the y value is 4. All right, now let's find the slope. Well, f prime of negative 2, now I'm plugging negative 2 in for my derivative. So 2 multiplied by negative 2, or in other words, negative 4. So I now know my slope is negative 4. Okay, so we have all the pieces that we need, even though you don't have the full credit for the problem, because the problem said find the equation of a tangent line. Let's proceed. Okay, so we're going to take this information, we're going to plug it into this formula, and then we're going to simplify it to get this equation of the line. All right, let's go ahead and do that now. So plugging in my point and plugging in my slope leaves me with y minus 4 is going to be equal to m, which is negative 4, multiplied by x minus, now that's minus negative 2. All right, so that double negative, right? So it's like your mom saying you cannot not go to the movies, right? So that contradiction, that negation means that we're going to have a positive x plus 2. So so for your notes, let me go ahead and rewrite this. So I have y minus 4 is equal to negative 4 times x plus 2. All right, well, you got it from here. Distribute the negative 4 and then solve for y. So I'll do that. Y minus 4 is equal to negative 4x minus 8. All right, and let's go ahead and add 4 to both sides. So I'm left with y is equal to negative 4x, and if I have negative 8 and I add 4, I have minus 4. Here it is. So if you were to go to Desmos or some graphing utility, so here's the graph of x squared. If you were to you could try this. If you went to Desmos, Desmos, try graphing in Desmos this function, this point, and this line, and you will see that tangent line running tangential to that point. Okay. All right. So far so good. Let's go ahead and just continue working. If you feel free, say, to pause the video and try some of these. Many of them are just especially part C is just a good one for being able to rewrite your function. But okay, so the good news is that even if your function has more than one term, you can apply your derivative term by term. What did I just say? I just said that you can use that power rule here, then use the power rule here, then use that derivative for a constant here. Let's do that now. So we want the derivative, so f prime of x is going to be 3x squared. I'm going to write this, again, since this is for many it's your first introduction, minus 4. All right, now that's x to the power of 1 minus 1. Okay, and then, of course, the derivative of the 5 is just 0. Now, the reason why I take a second to write 1 minus 1 is because notice that what we have here is 3x squared minus 4x to the power of 0. Okay? And anything to the power of 0, right? So x to the power of 0 is 1. Now, again, you can, I don't know if anyone has ever taken a second to tell you why is something to the power of 0 equal to 1, but let's just inquire just for a second. If you agree with me that x divided by x is equal to 1, then you agree with me that x to the power of 0 is equal to 1. Let me show you. So what is the exponent here? Well, this is x to the power of 1 divided by x to the power of 1. So x divided by x is x to the power of 1 minus 1, which is x to the power of 0. So hold on here. So if you tell me that x divided by x is 1, then that also means x to the power of 1 minus 1, or x to the power of 0, must also equal 1. Okay? So here is, you can bypass all these steps, and you can just write 3x squared minus, well, 4 times 1, or minus 4. Okay, so this is a good one to pay attention to, at least the very first term. How do you rewrite that so you can make your derivative easier? So let's rewrite it right now. So no derivatives yet. So g of x, I can rewrite that. Well, negative x to the power of 4 divided by 2. So if I took your age and I divided it by 2, wouldn't that be the same if I took your age and multiplied it by a half, right? To multiply by a half is to divide by 2. So dividing by 2, I can just rewrite this as negative 1/2 of x to the power of 4. In fact, I think you'll be happier if you start thinking about multiplying by a fraction as opposed to dividing. And it just, for me, I would rather multiply by a half than divide by 2. Nevertheless, from here, this is easy, right? As soon as you were able to notice that you can rewrite that, then we can proceed to take the derivative. G prime of x is equal to, well, 4 times negative 1/2 is negative 2x cubed, plus, well, 3 times 3 is 9, so that's 9x squared, and negative 2, or just negative 2 times 1, or just negative 2. All right. So this last one, again, is a good one just to pay attention to. If you don't mind, take a second, put away your phone, close the numerous tabs that you have open, and just take a second to look at this and tell me, how could you rewrite y? Think about it for just a second. Consider the question. Well, you could rewrite y as 3x squared divided by x minus x divided by x plus 1 divided by x. And now let's go through and simplify this. So that means we can rewrite y as, well, 3x squared divided by x is just 3x. And then x divided by x is 1, so that's minus 1. And if you recall, you can rewrite that 1 over x as x to the power of negative 1. Okay, so no calculus so far, just rewriting y prime. This is easy. So derivative of 3x is just 3. The derivative of negative 1 is 0. And the derivative of x to the negative 1 is going to be negative x to the negative 2. All right, so your professor is the only real requirement that your professor is interested in right now is that you don't leave any exponents as negative values. So you could rewrite this as 3 minus 1 over x squared. I want to make sure you understand what I just said. I am happy with this. I'm giving you a check, and I'm going to the next problem. If you were to look this up in the back of your textbook, they would probably rewrite that as 3x squared minus 1 over x squared. And how did they do that? How did they go from here to here? Right, or I should say from here to here. Well, all they did was, literally all they did was write this as 3 over 1 and then combine the fractions, right? So you would need to have like denominators. So you'd have to have an x squared here, and then that's how they got to the answer. So this, if you want to, this is a good habit to form, to go ahead and write your answer all under one fraction if it's not too tedious. But I'm just telling you, I'm happy with this answer at this step right here. Okay, so let's, what I've done for you is I have the derivative of sine and cosine, and what I want to do is, instead of me writing by hand this proof, maybe I can save yourself some trouble here, right? So save your hand a little bit of writing. If you'll just lend me your ear for just a minute, it won't take very long to go through this proof. So really quickly, let's start. So the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. Now, what all I'm going to do is I'm going to show you how you can take the derivative of sine of x and how you would, using that limit definition, and how you would arrive at cosine. Okay? Remember, I said that there would be at least one problem where you have to go through the entire limit definition, right? So let's go ahead and start. Maybe you get a trig problem that you have to use this. So, okay, so starting with the derivative of sine of x, if you just think of it as if you have f of x, in this case is sine of x. So let's start. So if you start with your difference quotient, remember the first thing you do is plug in the x plus the delta x. So that leaves me with sine of x plus delta x minus sine of x. Okay, now this next step, the way that we go from here to here, is all we're doing is there's an identity that you would have learned in your trig course. Would have looked something like this. So if you have sine of, let's say, theta plus alpha, that you can rewrite that as sine of theta times cosine of alpha plus cosine of theta times sine of alpha. Okay, so what I'm doing here is, remember that your sine function, the only thing that it understands is angles. So whatever x is, and whatever x plus delta x is, it's an angle. So in this case, you would have, just again applying this little rule off to the side, instead of having a theta, your theta would be your x plus delta x, and your alpha would just be x. Did I do that correctly? Yes. Okay, so wait a minute, I don't think I did do that correctly. My apologies. That's what happens when I start daydreaming for a second. So let me say that one more time. So in this case, your theta would be your x, and your alpha would be your delta x. That's what I should have said. Okay, so moving on, how did we get from this step to this step? I'm just using this particular trig identity. But now that we're here, let's just finish it. So what I'm going to do is I'm going to rewrite the terms. So I'm going to move some stuff around. So notice that I'm bringing my cosine of x, let's look at it over here. I'm bringing my cosine of x times sine of delta x here, bringing my negative sine of x in the middle, and then my sine of x cosine of delta x is off to the right. In other words, I'm grouping so that, and the reason is I now can factor out a sine of x. Okay? So once I've factored out a sine of x, this is what would be left. So, okay, and what I'm going to do at this point is I have a fraction with two terms in the numerator, and I can break that up from one fraction into two fractions. So now I have cosine of x sine delta x divided by delta x, and then I have sine of x times 1 minus cosine of delta x over delta x. So I've split it up into two fractions. Finally, at this stage, we can evaluate our limits. So notice that what I'm doing is the limit has to do with delta x, right? So I'm going to be plugging in 0 for delta x, but cosine of x, notice that I'm just going to write that out front, because what delta x does has no bearing on what cosine of x is doing. So the limit deals with delta x only. So what I'm doing is, from here, I'm just splitting it up, putting the part with delta x's attached to my limit, and the part without delta x's out front. Okay, so doing the same thing over here. I want to get anything with a delta x, and then anything without a delta x as factors. At this stage, you know this, the limit of sine of delta x over delta x as delta x approaches 0. This is from chapter 1. We know that that's equal to 1. And again, right from chapter 1, we know that that is equal to 0. So what I have is cosine of x times 1, which is cosine of x, and then sine of x times 0, which is 0. So what you're left with is cosine of x. Now, what is interesting, what is actually quite interesting, and I know that proofs are tough, okay? But what is interesting is you have topics of sine and cosine, and which are much older than the topic of the derivative, right? So you have a derivative. It's depending on the history book you read. So most mathematicians would say that both Newton and Leibniz discovered or invented, however you'd like to argue, the calculus at the same time independently. Truth be told, there was quite a few other mathematicians who were right there. Now, but that's so maybe 400 years ago. And then you have the ideas of cosine and sine, which date back millennia. So you have topics separated by thousands of years, 1,000 or plus years, and yet the derivative of sine is cosine. It's quite marvelous that it's that simple, and that, but thus is mathematics. So let's go ahead and practice those derivatives. Okay, so no more proofs for this video. We got do a few derivatives, then we'll do one application and we'll be done. Okay, so if you want to take the derivative of y is equal to 2 sine of x, it is that simple. You can the derivative of sine is cosine, so this is simply 2 cosine of x. That's simple. Part B is also very simple. Again, if you can just remember that to divide by 2 is to multiply by 1/2. Okay, so no derivatives yet. I just rewrote y. So now let's take our derivative. So y prime, well, the derivative of sine is cosine, so we just end up with 1/2 cosine of x. All done. Okay, so again, part C, we don't need to rewrite part C. Y prime, the derivative of x is just 1, right? That's 1, you know that. That's just, I've already explained to you about anything to the power of 0. And of course, the derivative of cosine is negative sine, so minus sine of x. So that's simple. Finally, let's do part D. So we're going to take the derivative term by term. This one doesn't say what the function is, so we'll just pretend like it's y equals. So therefore y prime, and let's go ahead and begin. So the derivative of cosine is negative sine of x. All right. The derivative of sine is cosine, so that's just minus pi over 3 times cosine of x. Hopefully that was fairly easy. Okay, so let's actually see if we can find some value in these derivative problems. So let's deal with some derivatives and problems dealing with motion. Okay, so in other words, you throw an object, you drop an object, something is moving. So let's go over some language, because if you've had physics, this would be if you've had physics before, this would be information that you are already aware of, but it's not a prerequisite to have had exposure to physics for this class. So first, let's talk about the position function. So I want you to understand that I'm not a physicist. I've taken a lot of physics classes, but I'm not a physicist, so I will do my best in defining these different functions. So a position function is as simple as, if you give the function a time, it will give you a position, right? So we use s of t to represent position function. So again, what are you plugging in? Well, you're plugging in times, and then what you get back out is position. Okay, so if you drop an object on top of your house, s of 0 would mean how high the object was at time 0. That's right before you dropped it. And then you would, as you plug in times, you would proceed to get heights until it hits the ground, right? But so we know that s of t is position, t is time. This particular position function is of value to you. Let's just make sure you understand it. So if you, let's say you drop an object, or toss an object, either way, the way that you could find its position or how high it is would be the following equation. So let's make sure we understand. So of course t is just time, say in seconds. The g, so 1/2 g, so the g has to do with the acceleration due to gravity, right? Now that could be in meters per second, that could per second, or that could be in feet per second. Either way, what we have is some constant acceleration, right? In other words, doesn't matter if you throw a heavy rock or a light rock up in the air, you have a constant acceleration of gravity pulling it back down to you. Okay, that same acceleration on either object. Okay, now the v sub 0 is your initial velocity. So if you just drop an object, then you don't have an initial velocity. V sub 0 would be 0. But if you throw an object, right, throw it up or down, you would have some initial velocity attached to your position. All right, and finally, you also have your initial height. So I'll say that again. Notice if you plug in 0 for time, right, well, this would all zero out, and this would zero out, and you would just be left with your initial height. So again, you're on your roof. I don't know why you're on your roof, but you're up there with a rock, about to drop it. At time 0, the height, the initial height is of the rock is the position at that time 0. Okay, so now the velocity function. The beautiful thing about these derivatives is if you take the derivative of s, right? That's just s prime. Well, the derivative of your position function is your velocity function. Okay? Now, again, there's a difference between speed and velocity, right? Velocity is a vector, right? It deals with displacement. So velocities can be negative or positive or 0. I hope to make sense. If you're up there on your roof, it makes it how fast that rock hits the ground, right? If you're up there on your roof, how fast that object hits the ground is going to matter if you throw the object upward, or if you drop it, or if you throw the object downward, right? So you could apply a negative or a positive or a 0 to your velocity. Speed is always it could be 0, but it's always the absolute value of velocity. Okay? Finally, so all we need to know is the velocity function is just the derivative of your position function. So I'm going to go ahead and take the derivative above. So if you take the derivative with respect to t, let's see what that looks like. Well, you would bring that 2 out front. So that would be half of 2. And then you would subtract 1 from the exponent. So that would be g t. And of course, if you take your derivative with respect to t of initial velocity times t, you would just be plus initial velocity. And of course, the height is going to be a constant, right? You might be 10 feet up in the air, 20 feet, but the derivative of a constant is 0. So this would be your velocity function. Okay, so your acceleration function is, and I'll go ahead and write this, acceleration function is, think of it this way. So you start with s, the first derivative would be s prime, the second derivative would be s double prime. Okay, so you have a function, you take a derivative, then you take a derivative of the derivative. Well, the good news is the second derivative of the position function is your acceleration function. Okay, I'll write it this way. your second derivative of position just means you take the derivative of velocity. So whatever this is, if you take the derivative of v, that would be v prime, which is acceleration. Okay? All right. Now, what we want, you could continue, this is not particularly germane to this, to our class, but you can continue taking derivatives like s triple prime would be, we have velocity, then acceleration, then the next function would be jerk. That would be the change in acceleration. Nevertheless, let's actually see this in action. Last problem. And I know this has not been easy, long video, but let's finish it. So let me read. So at time 0, a diver jumps from a platform diving board that's 32 feet above the water. Now it says see figure 2.21. I don't have figure 2.21, so I don't want any jealousy, but I'm going to draw you. So draw a picture. So here's our individual, 32 feet up on a diving board. Okay, I'll tell you what. Let's go ahead and give this individual some water. Otherwise, he or she's going to have a massive headache. So, nevertheless, so the diver is 32 feet in the air and above water. Okay. So, it says because the initial velocity of the diver is 16 feet per second. Okay. In other words, it's not like the diver just didn't walk off and just fall. You can think of it as the diver sprung up, right? There's an initial velocity off the diving board. So here is the position function. So there's s of t, is equal to negative 16t squared plus 16t plus 32. And I have it, slightly more advanced question, not super advanced, honestly, but I have a part C to this. I'm going to a little bit more advanced, but we don't actually have to do any work. You can just look at the graph. Okay, so we're given position. If it says S is measured in feet, so that's why we want negative 16 as opposed to meters. So S is measured in feet and T is measured in seconds. Okay, here we go. So part A says, when does the diver hit the water? Now let's translate this. Part A is asking, at what time does the diver hit the water? Or, at what time is height 0? Does that make sense? T equals what is this question? Well, to hit the water is basically stating that S of t is height, right? By the time the diver is in the water, the height of the diver, we're going to assume, is 0. So part A is not a calculus question. It just says, when does the diver hit the water? That's basically saying, when does height equal 0? Or when does S of t equal 0? So all we're going to do is plug 0 in for S of t. So now we have 0 is equal to negative 16t squared plus 16t plus 32. Okay, so we're going to hope that this factors, but if it does not factor, it's a quadratic. You could use your quadratic formula if need be. The good news is this does factor. So in this case, we would factor out a negative 16. That will leave me with t squared minus t minus 2. And t squared minus t minus 2, we can factor that a little bit more. So that would be negative 16 times t plus 1 times t minus 2. Okay. So again, you practiced factoring for all those years because it's kind of hard to pick a t-value that you could plug in to cause to equal 0, right, when it's in this form. But it's actually really easy to pick a t-value when it's in factored form. So let's go ahead and do that. So the good news is that just using that zero product rule, if I can make any factor 0, then the whole thing becomes 0. So do you agree with me that if you let t equal -1, then the whole thing becomes 0? Or if you let t equal 2, the whole thing becomes 0. All right, so mathematically there are two solutions. Only one of them has any meaning to our application, right? Mathematically, there's two answers to this equation, but I don't know what a negative time is. So we will go with t is equal to 2 seconds. All right, so the diver jumps. 2 seconds later, the diver is in the water. Okay, height is 0, 2 seconds later. All right, part B. It says, what is the diver's velocity at impact? Let's translate that. So that means when that diver finally hits the water, okay, 2 seconds later, what is the velocity? How the velocity that they're moving at. Okay, so if you hear slope, think derivative. If you hear velocity, think derivative. Or just in doubt, when in doubt, take a derivative. So we're going to take the derivative of this function, which is fairly easy. So -32t plus 16. Now we know that t equals 2 seconds, right, from part A. So if you want to know the velocity, s prime of 2 is going to be the velocity. So that's plugging in 2, we have -32 times 2 plus 16, or what? -48, in this case, feet per second. So there's two ways of stating this. The negative means, in our case, downward. So you could say the velocity is -48 feet per second, or you can say the velocity is 48 feet per second downward. Either one works. All right, part C, which is just my question. At 0 seconds, the height is 32 feet. At 1 second, the height is 32 feet. Explain to me how somebody jumps at time 0, they're 32 feet in the air, and 1 second later, they're still 32 feet in the air. Well, you see it from the fact that it's a parabola, the fact that they sprung upwards is why at 32 feet, at time 0, they're at 32 feet, and at time 1, they're 32 feet up in the air. All right, you guys take care. I'll see you in the next video.